For centuries, we have explored the universe using the laws of physics discovered by Isaac Newton and Albert Einstein. These laws have served us well, explaining the motion of planets, stars and galaxies. Yet, there are realms where these classical laws break down, realms of the very small, governed by the strange and counterintuitive rules of quantum mechanics. Quantum mechanics, the physics of atoms and subatomic particles, reveals a universe vastly different from our everyday experience. Here, particles exist in a haze of probability, capable of being in multiple states at once. This strange world, however, seems incompatible with Einstein's general relativity, which describes gravity as the curvature of space-time, a smooth and continuous fabric. This is where quantum geometry enters the picture. It is a field of theoretical physics that attempts to reconcile these two pillars of modern physics, quantum mechanics and general relativity. Imagine a world where space and time are not smooth and continuous, but are instead composed of tiny discrete chunks, much like the pixels on your computer screen. This is the essence of quantum geometry, a field that seeks to understand the very fabric of reality at its most fundamental level. Unifying quantum mechanics and general relativity is a major challenge in modern physics. These theories are successful but seem incompatible. Quantum mechanics describes the universe as probabilistic and quantized. General relativity describes gravity as a smooth, continuous property of space-time. Quantum geometry proposes space-time is quantized, made of tiny, indivisible units. Like light is both wave and particle, space-time may be granular. Imagine a piece of fabric. From afar it appears smooth and continuous, but as you zoom in, you begin to see the individual threads that make up the fabric. This is analogous to how quantum geometry views space-time. What we perceive as smooth and continuous is actually woven together from tiny, discrete units of space-time. These units, often called Planck units, are incredibly small, on the order of 10 to the power of minus 35 meters, far smaller than anything we can currently observe with even our most powerful microscopes. At these scales, the very nature of space and time becomes fuzzy and uncertain. Space-time itself becomes subject to the same quantum fluctuations that govern the behavior of subatomic particles. One of the key concepts in quantum geometry is the idea of quantum foam. This refers to the turbulent, ever-changing nature of space-time at the Planck scale. Imagine space-time as a bubbling, frothing sea of quantum fluctuations, where virtual particles constantly pop in and out of existence. This dynamic and fluctuating space-time is a far cry from the smooth, static space-time of classical physics. Pioneers of the quantum realm. The quest to understand quantum geometry has attracted some of the brightest minds in physics. One of the pioneers in this field was John Wheeler, who coined the term quantum foam and made significant contributions to our understanding of black holes and quantum gravity. Another leading figure is Roger Penrose, known for his groundbreaking work on the mathematical description of black holes and his contributions to twistor theory, a mathematical framework that could potentially provide a path towards quantum gravity. Abhay Ashtekar, a physicist known for his development of Ashtekar variables, provided a new way to formulate Einstein's theory of general relativity, making it more amenable to quantization. Carlo Rovelli, one of the founders of loop quantum gravity, has made significant contributions to our understanding of quantum spacetime and its implications for the early universe. These are just a few of the many brilliant minds who have dedicated their lives to unraveling the mysteries of quantum geometry. From theory to reality, applications of quantum geometry. Quantum geometry could revolutionize our understanding of the universe and lead to groundbreaking technological advancements. It could impact cosmology, particularly our understanding of the early universe. Quantum geometry could help us understand the Big Bang and the birth of our universe. It could also provide insights into black hole physics and singularities. Quantum geometry could shed light on the information paradox in black holes. It could pave the way for new technologies harnessing quantum gravity. Speculative technologies include warp drives and wormholes, concepts once relegated to science fiction. The future of quantum geometry. Unraveling the universe's secrets. Quantum geometry is a field brimming with potential, holding the key to unlocking some of the universe's deepest secrets. As we delve deeper into the quantum realm, we can expect to uncover even more profound and surprising insights into the nature of reality. The quest to unify quantum mechanics and general relativity is one of the greatest challenges facing modern physics, and quantum geometry offers a promising path towards this unification. By understanding the quantum nature of space-time, we will gain a deeper appreciation for the fundamental laws that govern our universe. We may discover new particles, new forces, and even new dimensions that we never knew existed. The journey into the quantum realm is just beginning, and the discoveries we make along the way have the potential to revolutionize our understanding of the cosmos and our place within it. A universe of possibilities. As we conclude our exploration of quantum geometry, it's important to remember that this is just the beginning of a grand adventure. The universe is full of wonders, and our thirst for knowledge continues to drive us deeper into the unknown. Quantum geometry is a testament to the power of human curiosity, our relentless desire to understand the world around us, from the smallest subatomic particles to the largest cosmic structures. So the next time you look up at the night sky, remember that the universe is not just a vast and empty expanse, but a tapestry woven from the threads of quantum space-time. And within that tapestry lie the secrets to our existence, waiting to be unraveled by the intrepid explorers of the quantum realm. Thank you for joining me on this journey into the fascinating world of quantum geometry. May your curiosity continue to lead you to new and exciting discoveries.